Hello, everyone. This is Spencer Snolling from Hatch, and thank you for joining us today for our monthly GPSX webinar. Myself and my colleague Jacob Barkley are here today. This is actually the second half of the two-part webinar series about the new features and models that are available in GPSX version 9, which just came out several weeks ago. And so we hope that you have had a chance to download it and take a look and are enjoying it. So the plan for today is, as usual, we're going to be running some simulations. We're going to be showing you some details and describing with some PowerPoint slides and demonstrations all of the sort of a bit more focusing today on the control features that we've got going and some of the new modeling content. So as usual, we will stay around at the end of the webinar to answer any questions that you have asked. So while we're going along, please type your questions in the chat, and then we will stick around at the end to answer those. I will just give you a slight heads up. In our preparation and rehearsals, Jacob and I realized this is a bit of a long webinar, so we might go past the 1 hour mark a little bit today. So just give you a heads up there. Okay. So our plan for today is to talk about first of all, the Australian water balance model that is going to be talking about our new runoff model that you can use to simulate storm flow from rainfall. We're going to talk about the other process control models. Those are the controller boxes that you can put on your drawing board. We have several new ones in GPSX during this release, and we talked about some of them last time, and we'll do the rest of them today. I'll talk about the oxidation reduction potential model, the ORP model that has been added to GPSX, and a few details about some of the other changes that we made to our regular biological activated sludge model and some of the other chemical models that we have, just to kind of round out and give you the sort of the full explanation of all the things that you can expect to see when you're using the new version. Okay, so what I'm going to do is very quickly just give you a refresher. This is similar to what I talked about in the last webinar, just on how to get your new version of GPSX. So several years ago, we switched over our licensing system, so it's now much easier to go through the process of getting the new version and get you up and running. So the way that you do that is open up your copy of GPSX that you currently have. So that would presumably be version 8.5. Go to the help menu and go to check for updates. You may find that this is actually automatically happening for you, that we did set these, depending on what your preferences are, such that it may check every time you open GPSX. So you may have already seen this message. It pops up a little window saying, hey, we have a new version of GPSX, and there's details about where to go and the links to download the software. So once you've done that, you install the software, and then everything else is just exactly like you've been doing so far. So the same email address and password that you are currently using for accessing version 8.5 will also now work for version 9 as well. And I have had a few people ask, can I keep old versions running? And that is absolutely true. You can. So if you're in the middle of a project right now and you're using a version 8.5 model and you just want to keep it there, that is also fine. You can have both versions installed and they won't interfere with each other. Okay, so another quick summary I want to make about all of the things that are in here in the new version 9 of GPSX, just in case you're attending today but did not catch the first webinar that we had 1 month ago. So in that webinar, we talked quite a bit about the interface features, the new interface features that are there, including the process benchmarking. So that is in the quick display panels that you can display for every object. We have a select set of parameters that are now going to be colored, and they're hopefully going to help you identify places where you may have entered in some incorrect information. And so we're trying to flag sort of egregiously wrong numbers so that you can catch something you may have entered in the wrong units, for example, just to help you get through and identify and bring your eyeballs to things that you should be looking at when you're setting up your model. We also have a simulation log window that kind of keeps track and gives you some other details about what you're doing, and any data that's being read in, if you have outliers in there that you would like to exclude or handle in a certain kind of way, all of that outlier logging will happen in that simulation log window as well. We also have some new scenario functionality that allows you to just manage your simulations and your data very much more easily. So there are these five new wastewater controllers. We talked about the proportional and the step controller last time. The three other ones we'll be talking about today: the weekly scheduler, the conditional controller, and the discrete event controller. We also have a number of new wastewater model content updates. So we're adding ORP, the runoff model that I mentioned before, a pipe delay model, and some changes to our chemical dosage model as well. And, the usual assorted updates to our various models and adjustments to calibrations and bug fixes and other minor things that we do every time around. So hopefully all of those steps, the theme to this release was to try and help people with the initial setup of their model, to get through and make it easier to get the model set up and running and do what you want it to do. So as a kind of an ease of use focus. So, as I mentioned, you can check out all of the details where we talked about benchmarking, data handling, process controllers, all of that stuff that was in the last one that Jacob and I did 1 month ago. You can come to our YouTube channel, youtube.com/hydromantis, and you can watch part 1 of that webinar series. And this webinar that we're doing right now will be up on Monday as well. Okay, so at this point, I'm going to hand it over to Jacob, and he's going to take it away and talk about the Australian water balance model.
Okay. Thank you, Spencer. As Spencer mentioned, the first thing we're going to cover in this webinar is going to be the Australian water balance model. And what this model is it's a new runoff model that we've added to our existing stormwater runoff model. Where prior to this, we only had a linear runoff model included in that stormwater runoff object, where that was just a very simple mathematical model that was using a parallel linear reservoir model for actually modeling what the runoff was going to be. So just a quick refresher of what that model was doing, so we can compare it to what the Australian water balance model is now doing. It was just a simple mathematical equation where we were adding a direct runoff reservoir and a indirect runoff reservoir and adding those to get our total runoff. So to do that, we are modeling this as our direct runoff being a first order decay equation where we are multiplying the volume of the direct runoff reservoir by a direct runoff decay rate. Then to model our volume in that reservoir, we just had a rate of change equation where we were looking at the amount of precipitation that was entering into that reservoir and then removing the amount of runoff that was leaving from it. Where the precipitation entering into the direct runoff reservoir was just the proportion of the total precipitation that was entering into that particular reservoir. Then we have the same sort of model for our indirect portion of the runoff. So what we're doing now is we have a Australian water balance model where I have a kind of graphic that we can walk through to see how this model works. So what this model is it starts with with a catchment area that's divided into 3 distinct zones. What these zones are is they collect the rainfall. So when we have a rain event, it starts going into this catchment area and begins filling up these 3 zones in the catchment area. So you can see our precipitation is going to increase and it's stored in these catchment zones. This will keep happening as the rain occurs, and eventually it'll start to overflow as it fills up those zones entirely, and then it will be directed to 2 other stores, a base flow store and a surface runoff store. So those 2 stores will then also begin to fill up, and this is where our runoff actually comes from. So just like in our linear runoff model, there is a first order decay equation that we're using to calculate the amount of runoff coming from each of these stores. So it's just depth multiplied by some constant. So that's going to give you your runoff, where it's going to have a different behavior, whether it's coming from the base flow store or if it's coming from the surface runoff store. Another thing that's added in the Australian water balance model that was in the previous model is we also have the option now for evapotranspiration. So you can have water evaporating out of this catchment area and not being introduced to the base flow stores and then leading to runoff entering the plant. So that'll decrease your catchment area, the amount of water in that catchment area. And all of this is modeled based off of the Australian water balance model created by Boughton in the paper published in 2004. So you can go reference that paper if you want a little bit more details on what the model is actually doing. But let's take a look at how it's actually implemented in GPSX. So like I mentioned, it's implemented entirely in our runoff model that we had previously. So this menu has been modified a little bit from what it was in the previous version of GPSX, as we added accommodations for both models to be available. So now we'll first take a look at the linear runoff model version of this menu. So when you want to use that linear runoff model, you select the linear runoff model from the runoff model option. You can specify what your catchment area is going to be, the amount of rainfall that you want to occur during that during your simulation, and then you can specify all of the various constants that are used in those equations that I showed on the previous slides. But if you want to use the Australian water balance model, you just change your runoff model option, which you can see here is now set to Australian water balance model. You once again have to specify your catchment area, your rainfall depth, and your evapotranspiration if you want to include it. And the model works fine if you just keep that as 0 as well. And you can also specify all of the various parameters of the Australian water balance model in this menu. So the catchment area fraction, how you want to split up those 3 zones, what you want the capacity of each one of those zones to be, the split between the base flow and the surface store. You can set what the surface runoff recession constant is going to be, so how fast it's going to drain out of that store. Similarly, the base flow recession constant, and then just the initial amount of moisture in each one of those various stores. All right, so let's take a look at a quick demo of actually using the Australian water balance model. So I'm just going to switch over to GPSX now. And we can see there's just a very simple plant that we're going to use for simulating this event. So we have a wastewater influent object, our stormwater object, where that's going to be using the Australian water balance model. Those come into the plant through this control splitter, where we're going to say that 4,000 meters cubed per day is the maximum that can be pumped directly to the plant. Anything in excess of 4,000 meters cubed per day is going to be sent over to the EQ tank. And then it just goes through a conventional activated sludge plant. So right now it's showing just a typical set of results. So this was 1 day of running the simulation using our default setup. So let's take a look at how we configured this stormwater object. So if we go into the flow runoff model option, we can see our setup here, our setup menu, and it's set up using the Australian water balance model. If we scroll down, we're using most of those default constants, but we did make a few changes to the depth. We made them a little bit more shallow just to make it a bit more of a pronounced event in this small example that we're doing. So let's take a look at the results of a typical operation. So in that first day, we just ran a 1-day simulation. We don't actually have a rainfall event occurring during this time. So this is just our typical daily diurnal waste flow pattern coming into the plant. If we take a look at this plot now, this is a plot of what is going through this control splitter to the plant. So you can see we're just sending all of the flow to the plant right now because our flow is less than 4,000 meters cubed per day, so our plant can handle it. This is a plot of what's going to the EQ tank, so anything going up this way, and right now it's 0 because we are below our threshold, so everything's being sent directly to the plant. This is a plot of what's entering into the primary clarifier, so right here is just a replication of our daily diurnal pattern right now. And then you can see our EQ tank volume. Right now, there's no volume inside of that EQ tank. It was empty at the start, and we haven't sent any flow to it, so it's still empty, and it has a maximum capacity of 10,000 meters cubed. Then finally, you can see this is the flow coming out of the EQ tank. We aren't pumping any flow, and there's no overflow right now, so both of those are set to 0. So let's actually see what happens if we have a rainfall event in this simulation. So I'm going to increase the stop time to 10 days, and I have a data file that's going to be driving the rainfall. So rain's going to start occurring at the start of the second day. So after we've done a 1-day simulation, we'll start seeing rainfall. So if I run that, you can see here our influent profile change. So now we have rain that's occurring. It takes a little bit of time to fill up those catchment area stores before it starts to overflow into our runoff stores. And then around the 2-day mark, you see we start to get runoff entering the plant. So that leads to our typical base flow here for our wastewater flow, and then an increased amount of flow entering the plant as this red line represents the runoff entering the plant. This is the flow entering the plant going through our control splitter. So you can see it caps the flow at 4,000 meters cubed per day. So anything in excess of that is being directed to our EQ tank, not directly to the plant. If we take a look at the flow to the EQ tank, you can see the rest of the influent profile can be seen here as we're directing it up through this stream to our EQ tank and not directly to the plant. And then taking a look at the volume of the EQ tank, you can see that it's increasing, but by the end of the simulation, it's about 8,700 meters cubed. So it doesn't quite reach the maximum volume of the EQ tank. So we aren't sending any flow out of it. There's no overflow and we aren't pumping anything yet. So it's just filling up and not entering into the plant. So let's see what happens if we modify our Australian water balance a little bit. So I'm going to increase the catchment area capacity of our first zone. So that's the smallest zone in those three zones. We'll increase that to 0.0042 meters instead of 0.004. So we can store a little bit more before we start to see that overflow and then eventually runoff. So if I rerun that simulation, take a look at the influent profile again, you can see we are still seeing runoff around the same time in the simulation, but it isn't as pronounced as our catchment area is able to absorb more of that water before creating it, turning it into runoff that's going to enter into our plant. So if we take a look at what's entering the facility through the control splitter, you see it is still capping at 4,000 meters cubed per day. And we are still sending some flow over the EQ tank, but it's not as pronounced as it was in the previous simulation as we have less rain, less runoff. And finally, looking at the volume of the EQ tank, you can see it doesn't fill up quite as much as we saw in the previous simulation because there isn't as much runoff, and it is only filling up about 2,500 meters cubed instead of the 8,700 meters cubed. So let's look at one final variation of this simulation. We'll change the base flow recession constant. So that controls how quickly the water comes out of that base flow store. Since it's very high right now, it's a very prolonged amount of time that the water is coming out of the base flow store. And you can see that by the long tail that the runoff has here in this plot. So if we decrease that down to say 0.95, 0.95, and there we go, 0.95, and then rerun our simulation for another 10 days, you can see that we do have a similar profile to what we saw in the previous example, so our very first simulation. But the amount of flow entering the plant is capped for a lot longer because we have a much more pronounced effect of flow entering into the facility, because it's leaving that surface store much quicker, so we have much more runoff. Similarly, we see our EQ tank has more flow going to it throughout the simulation, and our volume completely fills up. So at about 4 days into the simulation, we've completely filled up our EQ tank. So any flow in excess is now overflowing our EQ tank and being sent to the plant. And then if we take one look at what is actually entering into the primary clarifiers, you see it's exceeding much higher than that 4,000 meters cubed per day target that we wanted. It's actually going above 5,000 meters cubed per day entering the plant throughout that simulation. So that's not what we'd want to see in this case, but we can take a look at how the Australian water balance model will impact the amount of runoff we get by changing those various parameters. Okay, so I'm going to go back to the slides now. And we're going to take a look now at some of the new process controllers that have been introduced in this version of GPSX. So as Spencer mentioned at the top, if you're interested in the proportional or step controllers, those were covered in part 1 of this webinar series. So go back and take a look at those. We're just going to focus on the weekly scheduler controller, the conditional controller, and the discrete event controller in this webinar. So first, let's take a look at the conditional controller. So what the conditional controller is it's a way to allow you to implement control actions in your simulations where they're going to be based off the value of a logical statement. So those statements, they take the form of if-else conditional statements. So you can say, if this statement is true, then do this action, where if it's false, then do this other action. And this conditional controller object includes models to create logical statements using either one condition or two conditions, and then linking those two conditions through another logical operator. So let's take a look at the input menu that we have for this. So we're first going to take a look at the single conditional controller, so just one condition. This is what the input menu is going to look like for that controller. So you have a toggle to turn the controller on and off. You can set the controller sampling time, and this is going to be how frequently GPSX checks the validity of the statement to decide what the control action is going to be. You can set what the conditional variable is going to be. So this is going to be the full cryptic tag of what you want to create a condition on. You have 6 condition types available to you, where those are going to be things like less than, greater than, or equal to. And you can set what the value of that condition is going to be going to be looked at on. So for example, in this case, you're going to evaluate it based on, is this statement less than 0? And then we have the manipulated variable, where you enter in the full cryptic tag of the manipulated variable that you'd like to change based on this status, based on the evaluation of the conditional statement. You have a value that the manipulated variable will be set to when the condition is true. So in this case, if the condition was true, we would set the manipulated variable to 1000. It's important to note all the units in this controller are in unit SI. So it's going to use be setting everything in the base GPSX units. So it's important you make those conversions if you're using this controller. You then have the ability to set the value when the condition is false. And then finally, a value that will be used if the controller is turned off. So the manipulated variable will always be set to this value when this controller is turned off. Next, we'll take a look at the input menu for the two condition mode of the conditional controller. So once again, you have a toggle to turn the controller on and off and to be able to set the sampling time. There's now an option to set the logical operator between the conditions. So now that we have two conditions, you need to consider how they'll be evaluated together. So for example, we have and, where that means if you want a condition to be true, or the statement to be true, both of your conditions need to be true. This can also be set to or, meaning that if either of your conditions are true, then the overall statement will be true. Just like in the one condition mode, you have the ability to set up your conditional variables. So you can set the control variable, the condition type, and the value for both condition 1 and 2. And our manipulated variable then needs to be set up again. So you set up the full manipulate cryptic tag, the value when the statement is true, the value when the statement is false, and the value when you turn the controller off. All right, so let's go back to our GPSX simulation to see how we can implement this conditional controller. So we're going to use the same GPSX layout for this demonstration. So I'm going to switch over to this conditional controller scenario. You can see it's already configured with a conditional control object. So let's take a look at how that's currently being configured. So if I go into input parameters, control settings, we can open up the menu and you can see that we're using a two condition conditional controller. So right now that controller's on. We're using an and logical operator to link those two conditions. So our action for it to be true, both of these statements need to be true. What these statements are is we're going to look at the volume of the EQ tank, so what the volume is here. And for this statement to be true, the volume needs to be greater than 5 meters cubed. The second condition we have is going to be based on the flow rate entering the plant. And what we're going to say is if this flow here, what's being pumped into the plant, is less than 3,500 meters cubed per day, then the statement's true. If we're pumping more than 3,500 meters cubed per day, then the statement's going to be false. And what we're going to be controlling is we're going to control the pumped flow from this EQ tank. So when our statements are both true, then we're going to be pumping 500 meters cubed per day from the EQ tank. Otherwise, our pump's going to be turned off. So if the statement's false or if the controller's turned off, we're not going to be pumping anything from that EQ tank. All right, so let's see what happens if we run this simulation. So we're going to start with a 5-day simulation just to replicate what we were seeing in our Australian water balance model example to see what happens now that we have a controller. So just like before, you can see we have that wet weather event that occurs and we start getting runoff. And right now, the flow to the plant is being capped at 4,000 meters cubed throughout the entirety of the simulation because we have more than 4,000 entering. Right. And the amount being sent to the EQ can be seen here. So we're sending everything in excess of 4,000 meters cubed to the EQ tank. And finally, you can see what our volume of the EQ tank is. So it is getting to that approximately 8,085 meters cubed. And just one other visual is that this amount is right here. So we are sending 4,000 meters cubed per day at this point through the simulation. And nothing is being pumped out because we said that if our statements are both false, then nothing will be pumped. And even though we do have volume entering into the tank, our tank has volume, so that statement is true. We are feeding more than 3,500 meters cubed per day at this point in the simulation, so the overall statement is false. So let's see what happens if we continue that simulation. So So we're going to set it to 15 days so that our rainfall event the amount of runoff that we're getting can continue to decrease. And if I hit continue, you'll see that the runoff does decrease. So our influent flow is decreasing in unison with that. And the flow entering to the plant, so what's being pumped through our control splitter here, then starts to decrease as the runoff decreases, eventually getting to a point where it is less than 3,500 meters cubed per day around here. So if we take a look now at the pumped flow, so that's going to be this one here, you can see that it does start to pump at various times throughout our simulation. So these are going to be periods of time where both of our statements are true. So our flow entering through this control splitter is less than 3,500 meters cubed per day, and our EQ tank volume is greater than 5 meters cubed. And you can see that any point past about 2 days, we do have volume in the EQ tank, so that's going to be true. And as we saw in this plot, our flow entering the plant is less than that, so that results in these pumping periods. You can see the effect of what's entering into the primary clarifiers in this plot here. So since our settings are a limit of 3,500 meters cubed per day entering through the control splitter and pumping 500, you see we're still capping everything at 4,000 meters cubed per day at the most. But there are periods where our flow is increasing as we're able to pump flow into the plant from our EQ tanks. Okay, so let's see what happens now if we make a couple of variations to our conditional controller. So let's see what happens if we increase our pump rate from 500 to 1,500 meters cubed per day, for example, when the statement is true. So if I rerun that, you'll see that we're just going to recreate that same influent pattern with the same runoff profile. The amount going through our control splitter isn't going to change. It's still going to limit everything to 4,000 meters cubed per day. And but the one major difference is now our amount that we're pumping from that EQ tank is increasing. It's no longer being capped at 500, but instead now we're pumping 1,500 meters cubed per day when both of those statements are true. And one interesting thing to note is that since we're pumping more, our volume is draining much quicker from that EQ tank. So we actually do fully empty the EQ tank before the end of this simulation, where we didn't in the previous simulation, but that comes at a cost. Now we're actually pumping 1,500 meters cubed per day from this EQ tank, but it's still limited on 3,500 meters cubed per day being pumped here. So that leads to periods of time where we can pump up to 5,000 meters cubed per day entering the plant into our primary clarifiers, which exceeds our target of 4,000 meters cubed per day. All right, so let's look at one more variation. So we're going to change that from an and statement to an or statement. So what this means is that pumping is going to occur if the EQ tank has a volume greater than 5 meters cubed, or if we are pumping less than 3,500 meters cubed per day into our plant through this control splitter. So if we rerun that simulation, you can see we have the same influent profile and the same pump profile as we saw in the previous simulation. But where it changes is now we're pumping flow from that EQ tank pretty much through the entire simulation. Because now as soon as we have volume in that EQ tank, so it's greater than 5 meters cubed per day, greater than 5 meters cubed, then we turn on that pump and start pumping 500 meters cubed per day. You can see that we do have volume basically right at the day 2 mark. So then our pump turns on at day 2. Okay, so let's move back to the slides once more to cover what is going to be our next controller. So it is going to be the weekly scheduler controller. So what the weekly scheduler controller is it allows you to define pumping control profiles based on the day of the week. So this is going to create a pump and control profile that's going to be repeated every week of the simulation. So you'll have a Monday profile, a Tuesday profile, and so on. And you're able to define the start time and the duration of the control event on each of those given days. So let's look at a quick visual of how this controller actually works. So I've done an example profile of what a scheduled controller could look like. So we have a defined profile for every day of the week. So let's say we start on a Monday. We would say that we have a Monday event. So at the 7th hour of the day, we'll start pumping at 180 meters cubed per day for 7 hours. And it'll have this profile here. Then the next day would be Tuesday, so we would replicate that profile because it has the same definition. This will be replicated for Wednesday, Thursday, and Friday. But then when it comes to Saturday, we have a different definition. We don't actually have any pumping during that time, so we don't start the event, and we have a value of 0. So when it comes to Saturday, we won't actually pump anything using this controller. And then the same thing will happen for Sunday, and then we'll loop back to Monday, so you'll see that we'll recreate that Monday pumping event again. All right, so now let's take a look at how you actually configure one of these controllers. So we have the just one input parameter menu that you're going to use to set up the controller settings menu that looks like this. It has a on and off switch to be able to toggle that controller on or off. We allow you to set up to 5 cryptic tags that you want to be pumping. So you can have up to 5 pumps defined in one weekly scheduler controller. We have the default pump flows, where what that is it's going to be the value that is pumped from each one of those defined pumps when not in a scheduled event. So if you're not in a scheduled event right now, it's going to be pumping 0 meters cubed per day. If I set this value to 50, for example, then when we're not in a scheduled event, it would be pumping 50. And there's one of those default settings for each one of the cryptic pumps that you define. Then the final place to set this up is in the scheduled pump flows table. So if we open up that table, you can see what it looks like. We have a column at the start. So this is an uneditable column where it specifies the day of the week. So that's just to inform you what each row corresponds to. You can set what the start time of the event is in hours into the day. You can set how long that event's going to occur in a duration number of hours. Then you can set up a profile for each one of the pumps that you're going to be setting up in this controller. One important thing to note is that this is based on the day of the week, and GPSX has a calendar functionality actually built into it, so you can control what day of the week you're running your simulation from. So to access this, click on the Site Properties menu that shows up in the top left of the drawing board. Then you're going to navigate to the Simulation Setup tab of the Site Properties menu. You'll see this date and time at t = 0, and if you click on the button, it's going to open up a menu like this. This specifies what date GPSX will start the simulation at, and it knows what day of the week it is based on the date that it starts from. So by default, all simulations are going to start on January 1st, 2019, but you can enter in any values here, and GPSX will be able to tell what day of the week it is. So let's go back and take a look at one final desktop demonstration for this controller. So we're going to open up a new GPSX simulation for this. This is just a very simple plant. So we have a conventional activated sludge plant where the wastage sludge is being pumped to a sludge holding tank. That sludge is then pumped to a thickener, where the thickened sludge is then sent to a thickened sludge holding tank where it also mixes with the primary sludge. Then all of that is sent to a digester, and then a centrifuge, and the salts are removed from the system. So we have a dewatering scheduler controller set up for this simulation. So if we take a look at the inputs to see what it's doing, you can see the controller's on, and we have 2 pumps that we want to control with this scheduler. So the first is going to be QCon31, which is going to be the pumped from this sludge holding tank here. So we're going to schedule what rate we're pumping out of this sludge holding tank. The second one is going to be the pump from the thickened sludge holding tank, so we can also schedule how frequently we're pumping out of this thickened sludge holding tank into the digester. If we look at the default pump flows, we can see that when these events are not happening, it's going to be pumping a value of 0, so we're not pumping when we're not in an event. And if we take a quick look at what our schedule is, you can see that we're pumping Monday through Friday, but we aren't pumping on Saturday and Sunday. When we are pumping, we're starting at 7 in the morning, and we're pumping for 12 hours to 7 at night. We're going to pump 110 meters cubed per day from the sludge holding tank and 35 meters cubed per day from the thickened sludge holding tank. So let's see what the controller actually does. If I run a simulation where it's going to be a 14-day simulation, you can see that we are doing a scheduled event. The scheduled event is working. So it starts on a Thursday, then a Friday, and then we have a period of time here where it's not pumping because these are Saturday and Sunday before the Monday rolls around, and then we have 5 days of pumping and then 2 days not pumping, and so on. That profile will be repeated. Now, if we take a look at the volume in the sludge holding tank, so that's this one here, you can see that when we are pumping, the volume decreases, and when we're not pumping, the volume increases. So on Thursday, Friday, we have both of those patterns for 12 hours a day. Then we reach Sunday and Saturday where we have no pumping out of the tank, so the volume does increase. Then we have our 5 days of the week where we're pumping, and then that profile is repeated. You can see right now this volume is roughly in steady state where we're just replicating that same pattern over a 7-day period. We're not really increasing or decreasing the volume. We're just getting back to that same point at the end of the week. Similarly, you can see that same sort of profile recreated for the thickened sludge holding tank. So we have our repeated profiles of 35 meters cubed per day being pumped out. And once again, we're more or less matching the amount of sludge that's entering as what's leaving. So we're just kind of recreating that profile over the 7-day period. So let's look at a new scenario to take a look at a variation of this. So for example, what if we want to do a 4-day pumping schedule? So I'm going to open up that controller again and take a look at the schedule that we've defined. We'll still have the same start and end times and the same pumped rate. But where it's different is we're no longer pumping on Monday. So we could say that this could be to replicate a holiday or a 4-day work week or something like that. But for whatever reason, we aren't pumping on Mondays anymore. So if I run that simulation, you'll see that once again, we start on a Thursday and Friday. So we have our profile occurring. But this period of time with no pumping is a little bit more extended because now this covers Sunday, Saturday, and Monday. Our pumping starts again on Tuesday and carries on to Friday. And then we have another 3 days of not pumping before reaching Tuesday and continuing that profile repeatedly. So if we take a look at the volume changes in the sludge holding tank, you can see Thursday, Friday, we're removing sludge. So our volume's decreasing, but then we have an extended period of time where we aren't removing sludge, so that volume does increase. Then we have our 4 days of removing sludge, but since we aren't really matching the amount that's entering and leaving anymore, the volume of this sludge storage tank is now increasing, and eventually we will completely fill this tank if we don't change our pumping strategy that we're using. Then you can see the same sort of profiles in our thickened sludge tank where we are, once again, since we're only pumping 4 days a week, we are starting to fill up that tank and will eventually reach its full capacity. We have one final scenario that we want to take a look at with this controller is what happens if we extend the amount of time that we're pumping for. So if I once again open up the schedule and take a look, you can see that we are now pumping on Monday again and not pumping on Saturday and Sunday. But we're starting much earlier in the day. So we're starting 4 hours into the day and we're pumping for 18 hours instead of 12. Our pumped rates are the same, but it's going to be a much larger volume being removed from the system because we are pumping for a longer period of time. So let's run that simulation to see what happens. So if we take a look at our pumped profile, you can see that it is pumping on Thursday, Friday, skipping 2 days, Saturday, Sunday, and then starting again on Monday. But you can see that there's less time in between these pumping periods because we are pumping for much longer. So there's less time of no pumping on those weekdays. Another important thing to note is that actually, as we get into that second week of pumping, we actually have to drop down the rate to about 40 meters cubed per day, which is the amount of wastage sludge that we're generating. That's because if we take a look at the volume in that sludge storage tank, we're actually completely emptying it out by that second week because we've increased the amount that we're pumping and we're no longer matching what's entering into the sludge holding tank. So we have to reduce the amount being pumped out to match what's coming in. You can see the same sort of behavior in our thickened sludge tank as well. All right. With that, I'm going to hand it back to Spencer now to talk about the next controller.
Thank you, Jacob. So I'm going to talk about the last of these new unique controllers that we have created, what we're calling the discrete event scheduler. So this is something that allows you to very easily set up a temporary change to a parameter that happens in a certain period of time and extends for a certain length of time, a certain duration, and then goes back to its original value. So this is not completely different than what Jacob was just showing you, but this is one important difference here is that this is a completely one-off thing. It'll do it once and then not again for the rest of your simulation. So the idea here is that we wanted to make it easier for people to investigate what happens when a certain discrete event is happening. So a change to your influent or pumping down a tank, or actually it doesn't even have to be pumping. It's actually, you can change any parameter at all in GPSX. So one of the examples I'm showing you here will be a toxic event. So we're going to change the actual growth rate of one of the biomass types there. So the key thing is it's a one-time event. You can specify when it starts, what that parameter value change is, and then how long that happens. And they can either be a fixed constant or it can be a randomly generated number. So we can do a little bit of uncertainty analysis with that. So what you do is you put this down on the drawing board, just like some of the other things that we were just showing you. And then we need to specify, first of all, the parameter it is that you are going to change. You can turn this on. You can specify this cryptic variable name here. And then the first thing is, what is the value that you want this set to when the event is not happening? So this would be kind of like your default value. And then there's 3 pages where you can specify, first of all, the timing when it starts. So that would be either a fixed or randomly generated start time. You can then specify what you want the magnitude of the parameter to be at the time the event is happening. And that, again, can either be set as a constant or a randomly generated number. And then the same thing for the duration. So once the event is finished, it will go back to the value that you specified here at the top. So it's just change and then go back to its original value. Okay, so I'm going to show you a couple of examples here. First one we're going to do is a pumping event. So this is going to be a little bit like what Jacob did, sort of draining a storage tank with a high concentration wastewater, and that's going to go into the head of this particular activated sludge plant, and we can see what the effect is on the effluent. And then the second one is going to be a temporary reduction in the growth rate of the AOBs during some event, in which case there's some toxic thing is coming through and it's affecting the biomass. In this case, we're going to take advantage of the randomly generated aspect of it as well, for a randomly generated start time and then randomly generated duration. Okay, so let's start with taking a look at this plant. It's a very simple, straightforward plug flow activated sludge plant. I left out the biosolids handling part of it for now, just for simplicity's sake. And I put 2 of these discrete events on here. Now we're only going to have one or the other on at a time so that I can explain these 2 different things. So let's go over to modeling mode, and I set up 2 different scenarios, one for the pumping event. So we've turned this one on and this one is off. And here we can see that we have an event that's going to start at 0.8 days, and it's going to happen for 1 day, where we're going to turn on this pump controller here. So if I open up this menu, we can see that I've got this cryptic variable name, which came from this menu here. As you may know, if you ever need to find a cryptic variable name to go into a particular location, you can always just right click on anything on the menu, just coptic that cryptic variable name and then paste it in here. And right now, by default, it's going to be at 0. So we're not pumping anything out until the event happens. And then at 0.8 days, we're going to set the pumping to 500 meters cubed per day for a duration of 1 day. So that is going to be very simply just show you right now. And by the way, we're starting with 500 meters cubed in here. So if I just run this simple, we can see that what it does is 0.8 days into it, it pumps that 500 meters cubed out, and then it returns back to its normal value. So that is pretty straightforward, and we can take a look at how this affects the effluent concentrations here. I set this up so that this sludge here is a really high solids concentration. We can see it bumped up TSS here. It's an increase, I don't know, maybe about 15% or so, 15-20%. And what we can do then is, with this nicely organized way of making this event happen, is we can investigate that with some parameters up here. So I could, for example, say what happens if this was, say, it was a delivery of some waste, and we had a little bit of control over how long and that's going to happen for, and what intensity. So we could use this to investigate different options. So say we had this 500 meters, then we had to get this into the plant over some period of time. Let's say we do it at for half as long at twice as fast, right? So that's still going to pump down that tank and completely empty it. And if I go back and look at that, we can see here it pumped it down real quick, just half as long as before. And of course, it does have an effect on the solids in the effluent here as well. So now instead of bumping up here, I think originally that was like 15% increase. It's now looking at like about a 40% increase. So basically you can see that it's not quite a linear relationship, but you can see the effect that that is going to have. We could even go, of course, the other way. Any combination of these two numbers that adds up to, when you multiply them together, it gives you 500. So let's go, in this case, let's go for 2 days at 250 per day, and then we'll rerun that. And then now you can see if we, as you would logically expect, if you spread that out over the duration of a couple of days, it has a much less impact on the plan. So I've had projects that I've worked on with clients before where we were talking about doing these sort of discrete events where a septage delivery happened, or we had this tank that had to be pumped down over a weekend or something. This is the object that you could use to make that happen quickly and easily. You could always, there's other ways to do it in GPSX. You could read it from a file, or you could write your own code. We now have this drop this object on the drawing board. I think this is now the easiest way to do it. And if it needs to be something that repeats, then you would use the other object that Jacob just showed you, the weekly scheduler. Okay, so that's basically looking at an operational parameter. I'm going to flip over to the toxic event now. And in this case, we are going to be adjusting a growth rate parameter. So I'm going to just show you what that looks like very explicitly here by running this 3-day simulation. And this is the value of the AOB maximum specific growth rate. It's 0.9, and then goes to 0 for a period of time, and then back to 0.9. That's a fairly crude way of making something really bad happen to the bugs for a short period of time, and then they recover. So what did that do to the effluent? Well, let's take a look here. We can see that, of course, the ammonia spiked way up during that time. And that was, of course, because there was no nitrification happening suddenly out of nowhere. So what we can do in this case, though, is I've set this up so this is actually a random event. So here's that cryptic variable name. This is the value I want it to be when the event is not happening. So it's regular default value. And then a randomly generated start time with a normal distribution with a mean of 1 day and a standard deviation of 0.5. Then when the event happens, it goes to 0. And then when it's done, the duration of that event is also randomly generated to be 0.75 days as a mean with the standard deviation here. So ultimately what that gives us then is the ability to just keep running this over and over again. And as you see, you get different results. And that is because the duration, time, and effect of this particular event is being randomly generated. Okay, so that begs the question, how is that useful to me, right? So the reason I like to use this particular approach is that this is very much, toxic events are really hard to define. You don't obviously know when they're coming usually. And they're also, you may or may not know what's actually causing them. So if you want to understand what is the effect on my plant of something like this happening, you could do a test like this where you could run a number of simulations with some sort of event that you're going to force to happen. But since I don't know if it's big or small or whatever, I could, define it in this kind of uncertain way and then apply your uncertainty analysis by doing this. So just by standing here and clicking this over and over and over again, that's basically like a manual version of running a Monte Carlo analysis. Now, we actually have that built into GPSX as one of our standard forms of doing a sensitivity analysis. And I have several other webinars on our YouTube channel where we talk about probabilistic design and using Monte Carlo or other features to be able to do sensitivity analysis. And I won't run it right here now because, of course, you do have to run a large number of simulations. But just to go back to the slides here for a second, I did run one previously yesterday where I looked at the total amount of mass that left the plant, the amount of ammonia. And so in essence, that's the area under that curve that was being generated. And you can see here when I did 500 of them, and then we collected them up and we looked at what that distribution would look like. And it's a little bit of a log normal thing here coming out. Okay, just to give you an example or a flavor of what that might look like. Okay, so I'm going to move on from that to talk about a few of the other new models that we have available in GPSX in version 9. One of the more interesting ones that's been added now is an ORP model. Basically, we've had requests for this actually for many years, and we didn't quite have a good way to implement it until recently on some work that we did. So just as a really quick refresher, the ORP is basically a common measurement that you can make of a particular reactor, and it is a measurement of the constituents of the wastewater to understand the amount of reducing or oxidizing agents that are there. So essentially, it's kind of a measurement of electron acceptors and donors. The most important part is not really that detail, but like, how is it useful to me? It basically is a measurement of whether something is an aerobic environment, an anoxic environment, or an anaerobic environment. So just cutting to the chase, this is the kind of thing that most people want to be able to predict with the model in some measurement or another. So this is measured in millivolts, and you kind of had these rough ranges where anything that's kind of 100, 150 or greater is considered aerobic environment, where you would have your regular aerobic growth, activated sludge, nitrification, and so on. An anoxic environment where it would be from minus 200 up to 0 or a bit above that, where you could have denitrification, and then fully anaerobic environment, where you would need that for doing BioP or for having your anaerobic digestion and methanogenesis and so on. So you can measure this in reality, so it'd be nice to be able to predict it in the model as well. Okay, so the reason we didn't have this prior to now is that there's really not actually enough information in the regular ASM type models that we are using in our industry here to be able to explicitly calculate all the elements of ORP in the way that it would be measured in the plant. So what we've done is we've basically made a few assumptions, and we kind of rolled together a lot of the uncertainties and unknown things into a couple of parameters that will allow you to sort of calibrate your ORP predictions in the model to any measurements that you might actually have. And once that's done, we can calculate the ORP for any stream in that plant layout. Okay, so this is a paper that we had at the WR-MOD 2022 conference in South Africa. My colleagues Dan Song and Rajiv Goel and our collaborator Matt Gray put together this approach. Okay, so this is available only for the Mantis 2 and Mantis 3 models and libraries at the moment. We will be looking to, in the future, roll out a more elaborate version of this for the other libraries that contain sulfur as well, since that plays a role too. Okay, so you can find this in the same menu that you would find the pH and the alkalinity. So you can click on and right-click on any connection point in your layout and go to output variables and find the pH, alkalinity, and now ORP menu, and it will be down here at the bottom. So the model is in itself a pretty simple equation. We have the total ORP. It has contributions from oxygen, contributions from nitrate, and then an overall what we call base ORP that's kind of like all the other stuff we don't know. So as you can see, that base ORP is a base number, and then it's slightly adjusted here for pH as well. And the other two are basically a contribution from oxygen and a contribution from nitrate. And each one of these also has its own sort of half saturation approach, similar to the growth rate equations that we use in our model matrix. Okay, so these parameters are parameters that can be adjusted by you to calibrate the model and fit it into the data that you have. And these values are the ones that are going to be calculated by the model. So that allows you to solve and get an estimate of ORP. So you could take this ORP base number and just dial things up or down as required. Please note that in the if you actually go and get that paper, in that paper, we actually did have another aspect to it, which was a delay function to represent the delay in the sensor data that would be coming along. We did not implement that in this very first version in GPSX, but we will be looking to do something along those lines in the future. So let's take a look at what we can do here in GPSX. First of all, I just want to do a really quick demonstration of where you can find a lot of that information. So essentially, this is like we've added this new thing to every object in your drawing book. So I'm just going to run a very quick example here. This is actually a variation on our A2O BioP layout. So this is a plant here. There's an anaerobic tank, an anoxic tank, and an aerobic tank, and with the appropriate recycles to do A2O. And so therefore, these should all have different ORP values, right? So if I click on here, right click, go to output variables and go to this new pH, alkalinity, and ORP menu, you can see here that, so this is aerobic, so we would expect a positive number here, and we can see that that is the case. So for anaerobic, we would be expecting to have a negative number, and we can see here that is also the case, so minus 196. And then for anaerobic, we would also be expecting to have an even lower value than we did for the anoxic zone, and that is the case. In fact, the lowest number we could get is probably in the digester here, where it's sort of fully anaerobic after all of those days of HRT, and that's minus 240. This is basically controlled almost exclusively by that base ORP number, and so you could use that to kind of calibrate your model by making adjustments there. Okay, so that's how you find it. You can drag those variables, plot them, and do whatever you like. But one other thing I wanted to do was actually show an example with a controller that is based on ORP. So here we can make a controller that would control alternating aeration. So we would have something where we have one bioreactor, and we can turn the air on for a while, and then we can turn it off for a while. And that could be done many different ways under many different philosophies of operation. We've got actually several examples of this in some of our previous webinars about doing various forms of nitrification and denitrification, but this is another variation on that now that we have ORP. So the idea would be we will use the ORP signal to tell the controller of the aeration system when to turn the air on and off. So as it slides up to the positive side when it's doing nitrification, when it reaches sort of a maximum limit, we'll say, okay, that's good. Now you can turn it off. So basically, this little diagram that's right on the drawing here for this object basically describes exactly what we want to happen. So it starts with a high ORP and low ORP boundaries. And so as it moves up and hits the upper boundary, that's when we'll turn off the aeration. And then therefore, we will now be moving into first an anoxic zone and then potentially an anaerobic zone. And that will cause the ORP to go down, and then it'll hit the lower level in which we turn the aeration back on again. So very simply, that is implemented with our on-off controller. So let me get my other layout up here. So just to give you a real quick look here, if we go to the controller settings, I'm saying this is going to take a look at the ORP every 5 minutes. This is the control variable, and it's going to bounce. The sort of upper limit is 100, our lower limit's minus 250, and you can see here that it's going to change QCon air, which is basically our airflow variable. So when it hits the when it hits the low limit, it turns the air on, and when it hits the high limit, it turns the air off. Okay, let's go over and run a simulation. So let's run that 3-day simulation here, and you can see the ammonia and nitrate kind of going up and down as that moves back and forth between the aerated time and the anoxic time, and we can see the airflow going up and down and being controlled by this controller. So what we'll see here is this is the behavior of the ORP signal itself. So as you can see, it's bouncing back and forth between the upper and lower limits, and it's causing the aeration system to respond accordingly. So of course, the drawing that I was showing you before was a very hypothetical system. This is what it's actually looking like in reality. And it's interesting because you can see here that when the air comes on, it rockets up pretty quickly, and then it gets to this upper point, and when it hits here, it turns the air off, and you can see immediate drop. But it takes a little while for the, so this is the contribution of the oxygen. You can see it takes a little while for the denitrification to kind of, kick in and take over here a little bit. And then it really starts to drive that ORP down until it hits that lower limit, in which case it's going to bounce back up again. So it's a nice way to sort of, give an alternate variation on what you're doing. And, this, and by the way, this example that I'm showing you right now is actually part of our sample layouts menu. It's under the control section. You can see that ORP controller with this example. Okay, so a few other things we got going on in version 9 as well. Let me move back to the slides here. We do have another version of the delay, hydraulic delay model that happens between units if you need that. So it's in the connecting pipe section here. This is the part where you find all of the controllers and splitters and combiners. This bottom one down here is a pipe. It doesn't do anything in terms of treatment. All it really does is provides a hydraulic delay in between unit processes. So you, like under normal circumstances, we would be assuming that anything leaving the bioreactor would be entering the secondary clarifier instantaneously. So that is not always going to be the case. I mean, normally that's a quite reasonable expectation for something that is, a very slow system. It's not really going to change that much over the 5 minutes it takes to move downhill to the next tank. But, you may have a situation. I did have one project I worked on years ago where all of our influent data that we were using was actually collected at a pumping station that was like many hundreds of meters away. So there was actually a significant delay between the data we were using up there and what was actually happening at the plant. So you can use an object like this to represent that. So basically all you have to specify is the pipe length and the diameter, and then this number of outputs to be stored is basically the resolution of the changes that you would have. So whatever happens at the beginning end of the pipe, that one HRT later, that will be happening at the outlet side of the pipe as well. Okay, so that's kind of it for new models on that side. So as far as the existing models, we've made a few changes. We kind of always do this every version as it comes along. And one thing that we did do was we made a couple changes to the chemical dosage model. So actually, the model itself is the same. It's mostly just cleaning up and making it a little bit more clear on our menus exactly what the specification of the dosages are. So you may find that when you open up this menu now, some of the wording is a little bit different. We're hoping it's a little bit more clear now about what is actually being dosed under any given situation. We used to have this, the method before of having you can dose the amount of mass or you can dose the concentration that you're looking for. We've now added a third option, which is to dose by volume. And you'll see that it requires a few more parameters for you to fill in. Specifically, the solution density is one of those. So you may take advantage of that, and you may have to provide a bit more extra information, but that's also there for you to use in the future. And lastly, I'll speak briefly here about some changes to our default model calibration. So every time we release a new version of GPSX, we often update the default model parameter settings for things that we've learned since the previous incarnation of GPSX. As we apply GPSX to our own projects, we often make changes to those parameters, and we also update various parameters just to keep up with the technology and the evolution of products throughout our industry. So the only one that was of major importance this time around for version 9 is this carbon dioxide to oxygen KLA ratio. So this is part of the site's property menu, and this parameter is one of several that relate the gas transfer of other gases other than oxygen to that oxygen calculation. So as you're doing aeration of a particular system, you're also allowing for mass transfer of other gases out of the system typically as you're bringing in that oxygen. So these are ratios that we've had established for some time. And this ratio, we are dropping down from a higher number, I think it was 0.88, down to 0.2, based on a lot of experience that we've had over the years. Basically, what we're doing is we're updating it, we're reducing that number to not drive off as much CO2 from the wastewater and keep more of that dissolved CO2 in the liquid. And that, of course, then drives down the pH. So what we were missing, or what we were finding, was that that particular aspect of carbon dioxide being generated by the biomass and lowering the pH over the length of the plug flow reactor, that effect was not as pronounced as we would expect it to be, so we've changed this particular parameter. So if you compare your version 9 model with a version 8.5, otherwise identical, you'll find that probably, if you have the pH model turned on, that it will give you a lower pH. So I ran those two things side by side here, and you can see that in this plug flow tank, it was 7 at the front end of the tank, and as the biological activity was happening, the pH is coming down a little bit there. It's actually dropping to 6.7 in version 8, and in version 9 it's dropping to 6.3. So it's a small change. It doesn't really affect the biology all that much, but it does play a little bit of a role. If you have the pH model turned off, you'll see changes in the alkalinity instead. So just in summary then, for the entire webinar, version 9 has updates to both the software interface and the wastewater modeling content. Really, we were trying to focus with this release on improving the ease of model setup and use. So doing some of those complex controller things that we could always do before, we've now got those objects which you can drop on the drawing board, and they're there to help you do that in an easier and more straightforward way. We have a new, more complex stormwater runoff model that you can take advantage of. And we've also added that new ORP calculation as a standard feature across all of the objects in GPSX. So those things, combined with all of the stuff that we covered in the previous webinar, have sort of given us a nice new updated version, and we hope that you're enjoying using it. So thank you very much.